Hello everyone, my name is Weixing and I want to present our work employing machine learning for new particle formation, identification, and mechanism analysis. We want to provide insight from a 6-year observational study in the Southern Great Plains. First, I want to introduce how the actual fine particles form in the atmosphere. The left-hand side diagram shows how the small particles generated by nucleation and then grow by condensation and coagulation and then grow to a larger sizes into a CCN level and then leading to the contribution to the climate change and air quality. Traditionally, people use the aerosol size distribution plot to analyze and identify the specific banana shape as example shown in this plot. But there's a challenging using this manual identification. This is very subjective, labor intensive, and time consuming, particularly for the larger data set. So in this case, we prefer to have a more automatic or objective method. In this case, we want to use the machine learning method incorporating for the identification. And this slide shows a briefly introduction of the supervised machine learning curved random forest, which is what we used in our study. And this diagram shows an analogy of the principle of this random forest. If we have a basket, fruit basket, referred to a larger data set, and then can be divided into different data sets, which means a different trace, decision trace. And if we really want to identify the banana shape, as the example of this banana, and we can identify this banana by a range of their features such as color, shape, or weight. If we say the new product formation, that could be some features like relative humidity and temperature. So there's by the major voting, and we can select and classify the final class as either a banana or an apple or other fruit. So based on these mechanisms, we want to trying to focus on two primary objectives. First, use the random forest to automatic identification of new particle formation event, including 45 features. We have 44 particle concentration at the sizes range of the 4.8 to 22.5 nanometer with the 44 specific size bins. And we also include the new particle formation start time. The second, we want to understand to analyze the mechanism drivers and the new particle formation by using 12 features, including temperature, humidity, solar radiation, and more, based on their data availability and also they're relevant to the new particle formation based on the past literature research. And for our data, we select the 6-year data from 2018 to 2023 using the atmospheric radiation measurement arm in the Southern Great Plains SGP of Oklahoma, United States, with a focus of different seasons and years. And this is a plot basically based on our data. This is the banana shape. And by combining the SMPS and nano SMPS result. And this table shows the summarize of the new particle formation event occurrence throughout the 6 years. And we have an average of the 16% of the new particle formation happen days in a year. And here, this slide shows the method for the random forest. We have two objectives, and for each study, we have a data collection, model development, and model interpretation. We have input features, and then we have target features with new particle formation occurrence as 1 and no occurrence as 0. The model development, we have some data analysis, data process, data normalization, we have a training and testing, we have a cross validation, and we have the model evaluation. And the model interpretation, we have the feature importance and the partial dependence plot to understand how important of these variables. And the first result, this slide shows the model performance, and we look at the normalized confusion metric, we can understand how the model can correctly label one or mistakenly label one or correctly label zero and mistakenly label a zero for the prediction. And based on this normalized confusion metric and these four widely used equations, we can understand their performance of precision, recall, and F1 score and accuracy, this result. For the class 1 non-event and for the class 0 non-event and class 1 event, we compare these two results. We find out the result for the non-event is higher than the performance of the new part formation event. This is likely due to our original data set. We have imbalanced data with more data with the non-event and less data with event. So there's some varied result. But in general, this accuracy is pretty good for our further analysis. The second result, we do the feature importance ranking of the total of 45 features. We compared new part formation start time and another 44 specific size particle concentration at specific sizes. And because for each sizes, they can be in a very narrowed sizes, so we just grouped this a bunch of data in together to compare the grouped feature importance ranking. And we find out the smallest group, the particle concentration in the 4.8 and 6.8 range is the most critical factor, and following by the larger size range and even larger size range. And we also find out the new particle formation start time play an important role, and which means the new particle formation happened in a specific time is very important. And in this case, we want to see the new particle formation distribution and summarize the monthly and quarterly count of new particle formation occurrence in these 6 years. So this slide shows basically based on the manual identification, we do the data analysis to see their distribution. We find out at the June and August at the summertime has the least count of new particle formation, but the December to April at the winter and springtime has the most. And the 6 to 12 CST has the most count of new particle formation occurrence, which basically at the daytime. And specifically during the winter, we find out the second significant portion of new particle formation happened at the 12 to 18 CST is another daytime. And we also find the winter shows a notable frequency during the 18 to 24 CST, which is a nighttime, but based on the atmospheric stable that facilitate new particle formation that could contribute to a higher event happened. And another nighttime 0 to 6 CST shows 0 throughout the year. So basically the take-home message from this slide, we can see at the season level, we can see the spring and winter has the most occurrence happened, but the summertime has the lowest happened. And for the daytime has much more event than the nighttime for this specific SGP site. And we really want to understand how these environmental variables play a role and influence to the new particle formation. And the slide, we do the feature importance ranking of the top 6 features, and we can look at this result, find out the solar radiation intensity play the most important role in this SGP set, and following by the RH and temperature and so on. And collectively, these top 6 features account for 76%. And specifically for the each individual, how it play a role to the probability of the new part formation occurrence. And we here introduce the partial dependence plot for the marginal effect of individual variables, which means we can see how the individual variables play a role into leading to the new particle formation. And here, the solar radiation shows a strong positive correlation with new particle formation. Is due to their a strong sunlight leading to the strong chemical reaction. For the photochemical reaction, generate some sulfuric acid or some low volatility vapor to facilitate new particle formation. And on the other hand, relative humidity negatively correlates with the new particle formation. And with the higher moisture, there are larger condensation sink and coagulation sink. And the temperature has a minimal impact, and the total surface area has a negative impact with the on the new formation occurrence. With the total surface area increase, we can find out there's a larger condensation sink and leading to the less new formation event. And for summarize of our work, we using the machine learning model can achieve an identification accuracy of 1995% for the new particle formation event. We identify the primary drivers of the solar radiation, intensity, relative humidity, ambient temperature are very important factors for leading to the new particle formation at SVGP. And for the frequency distribution, we find out the new particle formation happened primarily at the winter and spring and very low frequency in summer. And this work can provide a model for planning and deploying the atmospheric research campaigns and help us to better understanding the new particle formation and growth. And here I want to thank you for your attention, and I would be happy to answer any question you may have. And thank you, our organizations as well. Thank you.